Last class, one of the students, Chandrasekhar, has asked doubts. So these two questions are from GATE 2020, GATE 2022, I think. Yes, the previous lectures are also available, Tanmay, and they will be made available actually in a later period from NPTEL. Okay, from the NPTEL team. So this was the question. Consider the recombination process via bulk traps in a forward bias PN homojunction diode. The maximum recombination rate is Umax if the electron and hole capture cross-section areas are equal. Which one of the following is false? So what was the doubt was the maximum recombination rate. So the thing is that when I tried to search it over books, I wasn't getting very specific idea. So I thought I just kept on searching and I found that it was there on internet when I googled it. But this formula, since I'm not an electronic devices person, I'm not a physics person, I don't deal with devices. Okay, so this formula was something new to me, which was actually derived from something else. So sometimes in GATE these kind of questions do come which are not directly adhering to the formulas you might have read, but you can always solve these questions with your intuition because you would have read something similar, and using that you can also answer these questions, which I had told you in the last class, that I have not read maximum recombination rate or something like that, but I have read about recombination rate, and from that I can have an idea about all these four options. So I'll just show you what I found out. So I found out that the Umax maximum recombination rate is given by this formula. Okay, so recombination rate is basically given by this formula. Okay, and N and P are electron and hole concentration, Ni is intrinsic concentration, tau N naught and tau P naught are the recombination lifetimes of electrons and holes that we had seen in the very first lectures, I think. Okay, so when Umax occurs when N is equals to P is equals to Ni e to the power V upon 2 Vt. Okay, so Vt is the thermal voltage and V is the biased voltage, the forward bias voltage, whatever biasing voltage you apply, so that is the V. From here we get a Umax as this Ni e to the power V upon 2 Vt, which minus 1 can be ignored, by 2 tau naught. Now tau is a time quantity, and in one more paper I found out that it can be replaced. So tau naught is nothing but 1 upon sigma naught Vth Nt. Okay, so if you now see sigma naught and Vth and Nt, where sigma naught is the cross sectional area, so it will be some like meter square. Vth is the thermal velocity of the carrier, okay, which is meter per second, and this, you know, Nt is the density of states, which is normally meter cube, 1 upon meter cube, right, or centimeter cube, whatever. So you see that all these uh, units will cancel out, and what you will get is 1 upon 1 by second, which is second. So that's why this makes sense. Okay, so the recombination time can be given out by this formula. So this is not normally what we generally study, right? But this might be, whoever would have designed the paper might have thought that it will be a different kind of a question, never asked, so they gave it. But even if we don't know the direct formula, we can have that with intuition. I will explain how once more. So right now this formula is clear to you, so you guys can write this down. Okay, and with this the Umax will turn out to be this, the box that I just drew. Umax equals to half Ni Vth. Vth is the thermal velocity, sigma naught e to the power V upon 2 Vt Nt. And from here you can now compare whatever your question had asked you. Okay, so Umax is directly proportional to Ni, Umax is directly proportional to e to the power V, Umax is directly proportional to the thermal velocity. Okay, and in the question it is asked, Umax decreases with intrinsic carrier density. So this is true. Umax is directly proportional to Ni. So if Ni decreases, Umax decreases. C option you see. Leave B for now. Umax depends exponentially on applied bias. Again true. With all other parameters unchanged, Umax increases with the thermal velocity. That also is true. But there is no such information that Umax occurs only at the edge of the depletion region. And that I had told you that even if you see the graph of the recombination of the carriers, you will find that there is no such thing that it is occurring at the edge of the depletion region. Okay. So this was the answer. So B is the answer, which is false. Okay. Now coming to the next question, this is a more interesting question and this could have been solved. So with the one-sided PN junction diode depletion capacitance is given, value is given, reverse bias voltage is given 0.2 volt, and 1 by CT square is shown, and they have asked the slope of the plot. Okay. So now the CD value is, CD formula is, we had studied that. So this was the formula I was talking about in the last class as well, that CD is given by this formula, under root Q epsilon by 2 times V naught plus VR, where VR is the reverse bias voltage, V naught is your built-in potential, NA by NA plus ND, right? Now in your question, just remember this formula, okay? Now in your question, they have shown you a graph, which is 1 upon CD square with respect to V, right? So now you have this formula, and from here you can find CD square, which I have written. So CD square is inversely proportional to V naught plus VR. Okay, and therefore 1 upon CD square is proportional to V naught plus VR, and your graph is what? The graph was 1 upon CD square, and here it was V, right? So that is why I have written it in this form. Okay, and you can have a proportionality constant K, which is nothing but the slope of the graph, which they have asked. Okay, so slope is K, 1 by CD square upon V. V is nothing but V naught plus VR. Now the problem in this question is that they have not given V naught. Okay, so therefore this is not a complete question, since V naught is not present. So if V naught is there, we can then find it and give the solution. Okay, and this was actually, the options are there, so I don't have an idea about how to do it after this, because V naught is something that I need and I cannot assume this value. Okay, so this is how these two questions were to be solved. So is it clear to both of you?
Ma'am, in the first question,
Huh?
what is a capture cross section? Whole capture cross section.
I did not see where.
It
Oh,
is
so that
written
is the sigma
if the electron
value.
and hole capture cross section.
It is talking about the sigma values that I had shown you, na, cross section, sigma naught, this value, this variable that is coming. Okay, so the thing is, Chandrasekhar, is these kind of questions, if you want to dig it, you will have to dig a lot. So this formula is basically called Shockley-Hall-Reed process. So you can go and read about it, okay, and you will definitely, or all the doubts will get clear. But the problem is that GATE is not about digging it in this manner, because this question may not be asked any time after this. That can happen, because I have not seen this question before, and this might not come after this also. So some things are very much like, they are only on research papers, and mostly they are not found in BTech level books also. Okay, normally they are dealt with in master level or maybe doctoral level, and they are normally not uh, taken care of. Okay, they are normally not included in the BTech syllabus. Sometimes those kind of questions come, and it happens that none of the GATE experience may solve it. It may happen that nobody is going to solve it. So you should not worry about those kind of questions that much. This I had told you in the first class also, that you have to be very clever while giving or appearing for GATE or preparing for GATE. It is a very clever exam. Okay, so if you want, you can delve. So that's why I have written it here, Shockley-Hall-Reed process. You can definitely read it. I'm not discouraging you, but don't read and delve inside it in the cost of your practice of other questions. Am I clear? So what you were asking, that you were unable to understand this question itself, right? So this is nothing but just a normal forward bias diode. There is some recombination happening and they are asking what will be the maximum recombination rate depending on. And it is just a formula which you have to see and see what the parameters are. Okay. So if I had to give this GATE exam, if I would have appeared, I may not have solved this question because I don't know maximum recombination rate. I'll be very frank. I'm not a physics person and I don't know the devices theory. I don't know that much. So I will just leave that question. That is fine. This is a 1 mark question. This can be left. Okay. So don't keep on digging into it on the expense of your practice test. Am I clear to you? And if you want to read
Yes,
more
ma'am.
about it and understand, you can definitely just Google search this process, and I think you will definitely get things and you can understand. In the generation and recombination theory, the questions that I had shown you in the second or third class, maybe, if you remember, those questions are what are important. Okay, so I don't know, I don't think the question is here. Just check. So we had solved some questions of recombination if you remember. So I think I'm not going to find it right now. So those are what are important. The numerical based questions where generation rate, recombination rate is given, lifetime of carriers is given, and you had also asked I think 1 or 2 questions related to the recombination rate. Those are what are more important. Okay,
Okay, ma'am.
rather
Ma'am,
than a
just
formula which is asked only once.
and the second question.
So second question already I had told you, right? This is a good question, but there is missing data. According to me, there is missing data. So I need the value of V naught to solve this. Okay. So second question you understood, right? What I had explained. I explained it
Yes,
in
ma'am. Yes.
first class also. So there is missing data in this. I need V naught. I don't know if only V naught because I cannot use 0 volts as V naught. There is always a built-in potential. So I don't know if I take 0.2, will I get something, because zero point 0.2 will be what? 1 by 100 into 0.2 is 1 by 200, which gives around 5 something. So option A is something 5 point something. So I don't know whether that is the answer or not. If I just take that to be 0 volts, but I don't know. Okay. So according to me, V naught should be given. So with this, we start with the MOSFETs. Okay. Again. And today I'll just quickly review, show you degenerated MOSFET small signal model. We will find out the output impedance, and then we will go on to solve some questions which had come. Okay. So what is a degenerated MOSFET? So basically you have a MOSFET and suppose there is a resistance here, RS. Okay. And then you have applied VDD here, there is something here. Okay, no issues. And here you are taking the opposite. So if you want, you can put a RD here or just leave it. So what is the small signal? We had seen in the last class, the small signal is plus minus VGS here, and here it will be GM, VGS, R naught or small RD, anything can be written. It is interchangeably used. Okay, and here, so basically I'll just draw this like this. Okay, VGS minus, and here you see the RS is from the source to the ground, right? So RS is from source to the ground and RS is here, right? This is clear. So now if I want to solve this, my V out is here. Okay. So two things can be found out. The total GM can be found out and the total impedance can also be found out. Okay. So what will be the impedance? Impedance is always the Thevenin equivalent. So here there is a Vn, right? Here there is a V. Sorry. This Vin is from this node to ground. Okay. So if I say that find out the Thevenin equivalent, what you will do? You will put a source here, VDC, and there will be a current flowing inside IDC, and at this point you will put V in as 0 volts. Right? This is what you will do. Carefully see this. Okay. So this is basically a ground, because you have to find the Thevenin resistance. Okay. So now you have to apply basically two equations, right? And can you guys, I'll give you guys time, you guys solve and tell me what you are getting VDC upon IDC. Please solve. I'm giving you time. You just solve. If you know network analysis, you will be able to do it. So please solve and get VDC upon IDC. Once you are done, you will let me know. Has anyone solved? So I want you guys to solve it. I will not say anything because last class we had done small signal. So I want you to do. No one? So it's a simple Kvl equation, right? So any equation that you have written? Chandrasekhar?
Yes, ma'am.
Yes.
IDC is equal to GMVH plus VDC upon RD.
How it is VDC upon RD? So RD is between this point here, drain, and between source, right? And VDC is from V out, this point drain to ground. So VDC cannot be IDC upon RD. Okay, so you guys have to practice network analysis a lot. Otherwise, these kind of things you won't be able to solve. Okay. So what will happen is, you see this is 0 volt. That means this is ground, right? This node is ground. So now from ground to this node, VGS exists, right? Okay. And this is entering current at IDC. Therefore, this current is also IDC here. Okay. So we can have some equations. So what we can do is, we will have two KCLs, I think. Yes. Let's have one KCL at node D. The KCL at node D, what it will do? KCL at node D will be IDC equals to GM VGS plus VDC minus of minus VGS. Is this fine? Please let me know. Because this node is minus VGS, right? This one. This node is minus VGS. So I have applied KCL. This node is V out, VDC, right? So KCL at node D. IDC equals to GM VGS plus VDC minus of minus VGS. Okay. So your first equation is IDC equals to GM times plus 1 VGS equals to VDC. This is the first thing. Okay. Next, see, let us see what happens. Next will be one KCL at the source here. Okay. So this will be what? So this can directly come. So VGS is nothing but minus IDC RS. Right. Now if I put what happens, put the values. I think I have missed here something. I have missed something. What is it? Oh, there will be RD here. No one is saying anything also. There will be RD here. So this will be GMRD. This will be RD. So after that, this will be RD. This will be RD. Okay, this is RD. And this is RD. Yeah. Let me just solve it once again from here. So one KCL I have put in D. Okay. So when I put the KCL in D, I get IDC equals to GMVGS plus VDC minus of minus VGS into RD. This current. Okay. Okay. So now the other current, other will be this one, right? So what that will be VGS equals to minus IDC RS, right? So I want what? I want VDC by IDC, right? So if I solve it now, what I will get? IDC equals to GM plus RD times VGS plus VDC into RD. Okay. And now you can put GM plus RD. Okay. IDC RS with a minus sign plus VDC RD as IDC. Okay. And I'm doing some mistake again and again, and nobody's pointing out. This will be division. That's why I wasn't getting things. This is 1 upon RD. Voltage divided by resistance is current, not multiplied. So I had multiplied. That's why it wasn't making sense to me. Okay. So now IDC is what? GM plus 1 by RD into VGS plus VDC by RD. Okay. Yes. Now it is fine. So now you can put VGS as IDC RS. So this will be minus RS GM plus 1 by RD into IDC plus VDC by RD. IDC. Here. Take IDC to one side. We will get 1 plus RS 1 plus GMRD, okay, by RD, and then VDC by RD, okay, and then you will get VDC by IDC equals to RD plus RS 1 plus GMRD. Is this fine? I'll just minimize it so that you can see the entire equation together. Okay, we have to find VDC by IDC. So I had done a mistake. I had written multiplied by RD in voltage. Voltage multiplied by RD and it's current, which is basically division. So voltage division with resistance is current. Okay. So this thing here is nothing but like this. Okay. This was a silly mistake that I did. So now I think it should be clear. So now let me know, you guys see it and let me know if you are able to understand this. This is the small signal model along with the MOSFET. Okay. Normally in small signal model we put KCL equations only. That is easier to solve. And you have to be very good in KCL and KVL. Okay. So first you should practice network analysis. Is this clear? So Jayesh, you have joined recently. Is this making sense to you? This is only calculation. I'm not asking about any theory or anything. Anyways, you were there in the last class as well. So please unmute yourself and answer. Jayesh, can you unmute yourself?
Hello.
Yes. Are you able to understand what I have done?
Yes, ma'am.
So what are we trying to find out? we are trying to find out the R out of the amplifier. Okay, this amplifier that I had shown here, this R out we are trying to find out, which is seen from here. And I have drawn the small signal model of it that we had seen in the last class. Okay, and now I am applying KCL equations to get VDC by IDC, because R out is nothing but the Thevenin resistance, and it is found with the Thevenin model only. Okay, so next is that we have, so after finding the R out, we will now find GM. So GM is given by I out by V in, and for that we have to short the output, as you can see in this small signal model. Okay, we have to short the output and V in will be applied, and this is the small signal model that we have drawn. Okay, so now I am redrawing this small signal model in this form. I am just doing a source transformation of this part. I am doing a source transformation here so that it is easier for me to solve the small signal model. Okay, so now we have two KVL equations. First is that we apply a KVL in this path, and therefore we arrive at this equation: V in equals to VGS plus I out RS. And then next is when we apply a KVL in this path. Okay, so you can follow this path or you can follow this path as well. Okay, both will mean the same thing. So I have followed this upper path and I have written this equation: I out RD minus GM RD VGS. Okay, so I out RD, this potential difference, minus GM RD VGS minus VGS plus V in is equals to 0. Okay, and on after that I arrive at this equation: I out RD minus VGS 1 plus GM RD equals to V in. And now I will substitute VGS from equation number 1, and after substituting I will arrive at this equation. Okay, and I out by V in will look something like this. So basically you have to remember your aim, you want to find I out by V in, so every other variable you have to substitute. So we arrived at 2 plus GMRD by RD plus RS 1 plus GMRD. 2 plus GMRD can be written as GMRD because GMRD is a very high value, and GMRD is nothing but the current gain, which is also denoted as mu. Okay, and the analogous thing is beta in BJT. Okay, and here I have just written approximate value of GMRD by RS plus RD plus GMRD RS. I have opened the bracket, and now I am taking common RD here. Okay, why we do like this? So as to arrive at a point where we can say that the resistor that was present with the MOSFET in the source of the MOSFET has actually degenerated the MOSFET. So this is called source degeneration. Okay, so this is the resistor is a source resistor which degenerated the MOSFET, leading to an increase in R out but a subsequent decrease in GM, and therefore we will see that there is not much change in the voltage gain. Okay, so the GM is approximated by GM by 1 plus GM RS. Okay, and what was the R out? R out was RD plus, this was R out, right? RD plus 1 plus GM RS into RD. That is what we found out, and now we found out this. So for 1 plus GM RS to be very, very greater than RD, we can approximate this result as GMRD. Okay, and this is the circuit. So from here we arrive at some conclusions. Okay, results. So you can see this is the first configuration where V in is applied here. Okay, and remember, whichever transistor V in you are applying, that will lead to the current here. Okay, the current here, which is basically GM times V in. So this is M1, so this will be GM1 times V in. Okay, this is GM1 and RD1. Okay, and the AV is given by GM into R out, and R out is nothing but R looking up. You can say this is R up, and R looking down, R down. So here basically let me do a clear diagram. So here if you see, R looking down is nothing but the MOSFETs R out. So this is RD, small RD, and R up is nothing but capital RD. Okay, and these two parallel, R up parallel R down, is what is R out. Okay, So that's why AB is directly GM RD parallel RD, capital RD you can write, and you did not solve any small signal for this. Now the second configuration is this, in which RD is replaced by another PMOS here, okay, which is properly biased, and there is a Vin. So again, as I said, the Vin is applied to M1, and therefore the current will be GM1 Vin. Okay, so the GM will be due to the GM1, and R up parallel R down is R out, which is RD1 parallel RD2. The third configuration is what we just saw, so I am not repeating that. Okay, the source degeneration. The fourth configuration can be that there is another RD present. So again, R up is this, and then R down is this. So you found out R down, right? So R down is what we saw in third configuration, this one. So this is nothing but the R down, right? So R down will be similar to that. So R down is this one, which I have written as R out. Okay, and R up is nothing but RD. So RD parallel R out is what I have written as the total output resistance. So let me write it that R out total. Okay, and GM, we have seen that GM will be degenerated. So GM1, this GM degenerated by the RS. So that will be constant. So you can solve the small signal and you see it is the same thing, because only RD has come in parallel. So it goes on to be like this, and you arrive at this equation, and this is approximated, can be approximated as RD by RS. Okay, so if R out is very greater than RD, which will be the usual case because of multiplying gain to RS, okay, and GM by 1 plus GM RS into RD, and that you can again simplify as RD by RS. This was the fourth configuration. Now the fifth can be that there is a this diode connected load, okay, and the diode connected load is always having a resistance of 1 by GM2, and this you can I think this we have seen in one of the class, okay. So and now this M1 this Vin is what is going to cause GM1 Vin. So basically the capital GM will be GM1, and the R out will be R up parallel R down, so 1 by GM2 parallel RD1, and this can be approximated as mod AB as GM1 by GM2. So like this I have shown you 5 configurations, but like this many more are possible, and you have to use your this conceptual knowledge to analyze these kind of MOSFET configurations or circuits. So this was the question that was asked. Okay, it was GATE 2020. Okay, so what is the resistance looking from the source here? We were trying to find out from here, right? But now this is from here, from the source. Okay, so quickly, small signal model. Okay, small signal model, and from, so this is not grounded, right? This is not grounded. What is grounded is this one. This is ground. Okay, and you have to find it from here. So I will apply a plus minus VDC in this point, because I have to find output resistance at that point, right? And you see there is this R here, capital R, 2 VDD, and in small signal all the DC sources are 0. So this is ground. Can you see the small signal? So VDD is 0 volts. So R's one terminal is 0 volt. The other terminal of R is connected to RD because that is the drain part. This is the drain, right? And the other end source of the MOSFET is open. So I have kept it open, and I have put VDC because I now need to find R out there. Okay, so they have asked Norton equivalent resistance. Norton equivalent resistance is the same thing as Thevenin equivalent resistance. The process is same. Okay, so now can you guys please solve this, because earlier that one I had solved. So now please can you solve? Here you can clearly see first KVL. What is it? VGS is equal to minus VDC. That is your first result. VGS equals to minus VDC is your first result. Okay, and then next can be a KVL at KCL at this point, at the VDC node. So if you put a KCL at VDC node, IDC is equal to VDC. Okay, so yeah, this is an interesting thing. So what you can do is, this can be simplified and can be easily solved. How to simplify and easily solve? So let me show that. This small signal can be now drawn as Is this clear to you, or should I explain what I have done? And this will make your calculation easier. Chandrasekhar, can you unmute and tell me what I have done? Have you seen this thing before?
Miller effect.
No. So
No.
basically, this is the simplest of. So I think you guys have not practiced network. First, Chandrasekhar, you should practice network. Forget about other things. Okay. First is network and signals. So basically, a voltage source with a series resistance. Okay. This is same as a current source with the same resistance, or with another resistance, say. I'll define what it is. Okay, and in this case, the value of the current is nothing but V by Rs. Source transformation, yes. Okay, so here the current source with the parallel RD is converted into the voltage source with a series RD. Sometimes this will make your job easier, sometimes. Otherwise, many times in small signal analysis, KCL only makes the job easier. Okay, so now, because now you can apply a straight KVL here, right? Straight KVL here. The current flowing is IDC, because here it is zero current. So IDC is the current. So now let's put the KVL. Minus VDC plus GMRD VGS plus RD plus R into IDC is 0. Right? So VDC is GMRD VGS plus RD plus R IDC. And VGS is nothing but minus VDC, we saw it. So 1 plus GMRD into VDC is RD plus R into IDC. And then VDC by IDC is RD plus R by 1 plus GMRD. And this was the answer. Now, if any one of you had gone through BJT, you would have seen a similar equation there. Common collector output resistance. Go and check it. I am not going to write it. And you will see it is similar to what I have written. GMRD is nothing but beta. GMRD is nothing but beta. Okay? Gain. Current gain. Okay, so similar thing you will see, it's a CC output resistance, and CC equivalent in MOSFET is common drain. So this was a common drain configuration because the output was taking in from the source, so common drain configuration. Okay, so I think I have to stop here only. I wanted to solve 2 more questions, but nah, somehow because I asked you guys to solve it, did not happen. So please be very good in network and solve the small signal analysis question, so that when you are going to, when you see this question, you should not need to draw the small signal model and find it. You should know it. Okay, and that will only happen if you practice that model.